forward. I think this video is going a little bit longer than I want it to, but that's okay. We're doing good stuff. So I just used that word titration, okay? And so what a titration means is we are reacting acid and base to the point of neutralization, okay? So I'll say neutralize. So we titrate out all the acid and base, or in other words, we convert all of the H plus and all of the OH minus into water. Now, this is, as I kind of briefly mentioned here, this shorthand. It's what we call the net ionic equation. We're gonna do a lot more practice with this. Okay. Our molecular equation gives me those full formulas, right? So the H plus was from HCl, and the OH minus was from NaOH. We know the H2O remains, okay? And what we canceled out from the net ionic equation was this NaCl aqueous. So technically, when we react a strong acid and a strong base, when we titrate them, we end up with salty water. So salty water is our product of an acid-base neutralization. And by neutralization, we're saying the solution is no longer acidic nor basic. It's just salty water, salty neutral water, okay? So to do this type of titration, we add what's called an indicator, and that indicator will change color under a certain condition. And there are lots of indicators. There's lots of chemical indicators out there. If we choose the right one for the particular acid-base reaction we want, it changes color when the reaction is done. It's pretty cool, okay? I think I have that, yes, I have that going on here. So right now what we would have, for example, is suppose here that in this flask is my strong base. In this burette is my strong acid, and titrating is this process of slowly letting this acid drip into the basic solution, into the base solution, and then now this thing right here, this medicine dropper, that is my indicator, okay? And we usually only have to put a teeny tiny amount of indicator. And if that indicator were phenolphthalein, that's this pink indicator that would be a good choice specifically for the HCl NaOH reaction. So we'll say good choice for NaOH plus HCl. And it's, you know, there's like dozens, if not hundreds of indicators. And we have to look at charts and to see like for which reaction would I want to pick the best indicator. You're not there yet. We'll be there in Chem 110. We'll eventually introduce that concept in Chem 110, okay? So this would be perfect. Just this ever so slight pink color for specifically this phenolphthalein would tell us that we have made H2O liquid and NaCl aqueous, so we've titrated out all the H plus and OH minus. This, too much, so we passed it up, okay? So this perfect condition right here that I'm showing you, this is called our end point, where the indicator has changed color. Let me see what my next slide is. Oh, I've got them right here. Okay, end point. The point reached when the indicator changed color, okay? But it's important to know that that's different than the equivalence point. The point when the moles of added titrant is stoichiometrically equivalent to moles of substance being analyzed. What does that mean? Well, that means that I have added HCl and NaOH in a perfect 1-to-1 ratio. Because you notice from this balanced reaction, they are 1-to-1. So the equivalence point and the end point aren't always necessarily the same thing. But if you've designed your experiment correctly, they will happen at a very, very similar point, okay? So if the titration has been done correctly and the indicator was chosen wisely, the endpoint and the equivalence point will be the same thing, okay? And so now the last thing that I want to do here is the sample calculation, okay? So this is stoichiometry. This is basically our reaction stoichiometry, okay? So I'm going to walk you through this thing, what I'm doing here. Instead of playing the music, I'll walk you through what I'm doing in this calculation, and that'll be it for this lecture, okay? So what volume of 0.1 molar HCl solution is needed to neutralize 25 milliliters of 0.350 molar NaOH? So I'll remind you that big capital M, right, means mole per liter molarity, okay? So first we have to get a balanced reaction. So we can see that it's HCl reacting with NaOH to make H2O liquid and NaCl. So we're making salty water, okay? And the really important thing of doing this balanced reaction is that we can see it's a 1-to-1 ratio. That's what's important, okay? So now what we're going to do is first figure out how many moles I need. Because basically in this reaction, right, we need the number of moles of NaOH to equal the number of moles of HCl. So for a titration, moles of base must equal moles of acid, assuming that it's a 1-to-1 reaction. Okay, for now that's what we'll deal with, just these 1-to-1 reactions. So I'm going to start by saying my 25 milliliters of NaOH, okay? Because when I have a volume and a concentration, that will give me moles. Volume, concentration gives me moles. Watch, check it out. I can say 25.0 milliliters of NaOH. I'm going to convert this to liters because I have the molarity thing going on. So I'm going to say 1,000 milliliters are in 1 liter. And this is how I can use this molarity, right? Check out how this works. Because I know it's moles per liter on top and bottom, and I really need liters to cancel, that 1 liter is 0.350 moles of NaOH. Okay, that's what that means. So when we see 0.350 M, you should be thinking 0.350 moles in 1 liter. Okay, and so now when I'm just going to do this calculation to show you what I get. Okay, so when I go and do this, here we go. Let's say 25 times 0.350 equals 8.75, and then divide by 1,000, and I get 0.00875 moles, technically, of just hydroxide. It's NaOH as well, but really it's the hydroxide that we want. And I also want to point out, we didn't have to use molar mass. Keep that straight. I did not have to use molar mass because I had a volume and concentration. Okay, when you think volume, concentration, I don't need molar mass, sweet. Okay, so now what is all this saying? Well, now I'm going to start with this number, and I'm going to say 0.00875 mole. I wrote OH minus or NaOH, right, depending on how you wrote the reaction. We'll stick with NaOH to be clear. So 0.00875 moles of NaOH. And now I'm going to use a balanced reaction. And the balanced reaction tells me 1 mole of NaOH reacts with 1 mole of HCl, okay? And now I have to convert that mole of HCl into liters. Well, look, I have a concentration of HCl, 0.1 molar HCl. So I can use it the exact same way I did here, but now I'm gonna flip it, okay? So now this has to be 0.100 mole of HCl in 1 liter of HCl. And the problem asked me for what volume, so I could leave it in liters if I want. But look, they gave me 25 milliliters up here, so to me, I think it's more reasonable to then make that a milliliter so that we're comparing apples to apples, right? So now I've got 0.00875. I left that number in my calculator so I wouldn't screw up the sig figs. And now all I have to do is take that number times 1,000 milliliters and then divide by 0.1, and I get 87.5 milliliters of my HCl solution. So what this means now, back to this original problem, okay, if I had, let me write this again, HCl plus NaOH. So if I had a 0.100 molar solution and 87.5 milliliters, and here I had a 0.350 molar sodium hydroxide solution and 25.0 milliliters, then I would perfectly titrate or neutralize the acid and base, and all that I would be left with is salty water. Okay, it would be neutral. No more acidic or basic properties. It would just be salty, neutral water. Okay, that is it for this video. I hope I stuck within my time frame. I didn't put a clock on, but I will for the next one. Okay, folks.